Great. Thank you very much for the introduction. Yeah, I'm a quantum person, and even more, I'm a kind of quantum information person. So if we kind of add nano meets quantum, I'm at the far end, deep into quantum. And that's why I'd like to start with kind of introducing some of the basics of photonic quantum technologies in the first part. And then I'd like to show some like recent results or topics we work on in my lab. So in general, single photons are very important for all kinds of quantum technologies. And even more, they're very interesting topics to study on their own in the context of quantum optics, quantum foundations, understanding the quantum world. And then we can bring this to quantum computing, quantum communication, networks, also quantum sensing in metrology. And the question for all these kind of applications is actually, how can we encode information in single photons? And photons are very nice systems. We have many different ways to do so, and these are just a few of them. So we can use different degrees of freedom, such as polarization, shown here, or not. We can use the path degree of freedom, and we can also use the temporal degree of freedom. And then the question of if we encode information, can we actually manipulate also the photon or the quantum system? And yes, of course, encoding information this kind of way also makes it easily possible to kind of manipulate the information. So we can rotate the polarization, we can kind of, by building small interferometers, we can tune the path, or we can also play with the temporal information of the photons. So this makes photons very nice quantum systems. But now, if we want to go to applications, for most applications, we want more than one quantum system. And for many applications, we also want to generate entanglement. And these are a few applications or a few examples where entanglement actually plays a role. And except for kind of single qubit quantum communication, you see that entanglement basically is relevant in all kinds of quantum technologies. So when you want to build photonic quantum technologies, we need entanglement. And the question is now, if you take two photons, how can you actually entangle two photons? What we do when building photonic quantum technologies is we often use an effect that has been mentioned before in the context of single photon sources, is we use the so-called Hongo-Mandel effect. And this means we kind of send two photons into a beam splitter and we measure here the output distribution. And now classically, if you send two classical particles into such a beam splitter, you would observe different kind of cases. So the photons would be measured on one output or the other, or one at each of the outputs. But quantumly, because of this Hongo-Mandel effect, we only observe these two cases. And using this effect now, we can kind of build optical quantum circuits. And it has been shown that we're actually using these kind of optical quantum circuits, we can in principle implement also universal quantum computing. And what you do is you have this is optical modes, you have beam splitters, and you have phase shifters. So this is a circuit with two qubits, you have some beam splitters, you have this kind of box here, which then turns into this box here. So by using these optical circuits, by using additional ancillar photons, by using measurements in a smart way, we can implement quantum computing. And as such, also implement entangling gates. This is a general picture, just an example of photonic CNOT gates. Here on the left-hand side, we see a photonic CNOT gate in this kind of path degree of freedom. So we have here in C, it's a control qubit, T is a target qubit, and we send the photons into the circuit here. We kind of post-select, very importantly, on a certain output distribution, and this creates an entangled state. And the same works also on polarization here. So in principle, we have photons in, photons out, and we do some kind of measurement here at the end. What we also see from this is that photonic quantum gates are different. So if you think of ion trap qubits or other types of qubits, you always have some kind of entangling gates between the qubits. And here we also have entangling gates, but they work in a kind of different way. And this also means, as we will see, that we also need alternative ways to perform quantum computing when using photons. In general, before we come to quantum computing, this was how we entangled 2 photons, but for many applications, we want to also generate large-scale entangled photonic states. For example, for those people working on these topics, cluster states, GHZ states. And we can do so by using the same principles as I've shown you. So we kind of generate single photons. We send them into kind of optical circuits. So this is just examples for experiments. And this allows us to generate large-scale entangled states that we can use for information processing. This is examples that use parametric down conversion sources, bulk optics experiments. This has also been shown to be possible in integrative photonics, and more recently also using using quantum dot sources to generate large-scale entangled photonic states. So this shows we can generate multipartite entanglement also with photonic systems. And at the end of my introduction, I'd just like to come back to the point on photonic quantum computing. So we see photonic systems are somewhat different, and this means photonic quantum computing is different. And just in a nutshell, usually when you have quantum computing, you have such a quantum circuit, which in some way resembles a classical circuit. You have inputs, you have outputs, and you have some kind of quantum gates here. And what we do in photonic quantum computing is actually look at different models of quantum computing, which are called measurement-based quantum computing. And what we see here is kind of many qubits. So these are the kind of circles. Then we have these lines. They mean entanglement. So what this shows is a large-scale entangled state. And then you can show that you can map any kind of quantum circuit onto measurements on such a highly entangled state. And by kind of taking the state and like in Pac-Man, you eat it up from the left to the right, you perform measurements, some feed forward, and you take here the last column here as an output. In this way, you can generate basically the same quantum circuit as in this model. We've shifted, however, from this circuit to this circuit, and this means now our challenge lies in generating these resource states and in implementing feed forward in the measurements. So this is universal quantum computing using photonics, also being implemented, but very recently another type of specific purpose quantum computer has gotten a lot of attention, the so-called boson sampler. Boson sampling is a way to kind of very easily implement some quantum computation, but only for solving a very specific problem. For those not familiar with quantum boson sampling, it's very simple. You take a linear optical quantum circuit, so the ones I've shown you here previously. You take some photons which enter, and you measure here the output distribution. And then you can show that you can connect the output statistics of this output here to actually the permanent of the submatrix here, and the permanent is a function that is hard to compute. So instead of kind of computing the permanent, you kind of sample from this distribution here. And there are several variants of boson sampling, one using kind of single photons, then you use kind of heralded photons when you generate photon pairs, and very recently using kind of squeeze set here, leading to a type of boson sampling called Gaussian boson sampling. And as said, these circuits are usually can be implemented in very different ways. For example, it's in integrated optics circuits where you have these coupled waveguides. Exactly. And very importantly, these concepts have led to kind of demonstrating a quantum advantage with photonic systems. So a task that has been computed with these boson samplers that was not be possible to compute in reasonable time classically. And on the left-hand side, you see the first experiment of such in a kind of heroic effort with a huge optical setup. So those working in kind of optics may know that this is kind of very difficult and a hard setup. This was the first photonic experiment to demonstrate a quantum advantage. And very recently here, you see a very elegant solution using actually the temporal degree of freedom and also demonstrating a quantum advantage. So this is kind of translating this experiment into time. Okay, so this is kind of what we deal with in photonic quantum technologies. And with that, I'd like to kind of come to my research and then to my group. So for us, the kind of central part is the photon. And we do experiments on exploring the photon, so in the area of quantum optics, studying interference, for example, of multiple photons with different properties, parameters. In the context of quantum technologies, we work on quantum networks, both on the hardware and the software. We work on quantum computing and also on photonic integration. And in the next minute or the rest of the talk, I'd like to kind of introduce some recent works on these kind of first two topics, and I say a few words towards the end on these other two topics. Good, so I'd like to talk about kind of three works we have been working on. The first kind of is on the kind of first topic, looking at interference itself. So how can we understand homomundal interference? What happens if we go to more photons? And I'd like to show you some interesting effects there. The second part is about a Bell state measurement, a crucial part of a quantum network. And finally, going a bit more into the computer science direction, talking about quantum protocols and communication beyond bipartite QKD. So I think I can just repeat this. For kind of all kinds of quantum technologies, we need single photons and we need reliable photon sources of pure and indistinguishable photons. And usually when testing or when building photon sources, as we have heard, the experiment to test the quality of photon sources is the homomundal experiment. And what you do is actually very simple. You take two photons, send them onto a beam splitter, and measure the output statistics. And then what you do is you vary. So you vary the distinguishability of the photons, for example, by varying the time, and you record such a nice homomundal dip. And this means that you measure the coincidence probability. So how often do you have a photon here and here? And when the photons are indistinguishable, this should not occur. So you get this kind of dip here. And then you can ask, okay, how can I describe this mathematically? And what we do here is look at the kind of simplest form. And you can show that this output statistics here is actually determined by the mutual distinguishability of the photons. So in simple words, by how different the photons are or how similar the photons are. And what you have here, you have basically the kind of this term here, and we take the absolute value here of the mutual of the overlap of the photons. So you take the overlap and then the absolute value, which gives you the mutual distinguishability. However, you see, we take the absolute value here, so any phases or so won't show up in this. And what we have shown some time ago is actually quite interesting, that when you expand this experiment to 3 photons, you take one more photon, you do exactly the same experiment, you vary distinguishability, and you ask yourself, what does this output statistic depend on? You can show that actually this in the 3 photon term, so when you look at 3 photon coincidences, you not just have the mutual distinguishability, but you also get a phase that shows up. And this phase is actually related to the phase you have in this overlap, which is quite nice. And this is one of the experiments we have been doing, and in general, there has been a lot of work on photon interference recently, also in the context of boson sampling. And this shows kind of very nicely that adding another photon here seems like a very simple extension, but you kind of get a new effect that you can't observe here. Good. However, so recently we kind of went on from this. And as an experimentalist, when you measure such a Hong experiment, you actually never get such a dip. But what you measure often is something like that. So it's not perfect. And then you could ask yourself, actually, why is that? So why don't I get a perfect dip? And most of the time you say, okay, my photons are not as distinguishable as they should be. They may be different in polarization, in frequency, or any degree of freedom. However, what you actually can show is that this dip can also be reduced, not only if the photons are distinguishable, but also if the photons are in a mixed quantum state. So you can you get this reduction in the visibility for two different kind of cases. And let me just explain you why this is the case. So I've told you the dip visibility depends on the overlap of the photons. And I said very kind of sloppily in the beginning, the overlap means whether two photons are distinguishable or not, or whether they're the same. But now if we look at this kind of in more detail, we see that the visibility actually depends on the overlap of the photons, but we can have, so this is kind of basically two vectors R for qubits. We can have two pure photons that have a certain overlap, but we can also have photons that are in some kind of mixed state, and as such, we also reduce the overlap. So these are just two vectors on the plus sphere, and we ask how much do they overlap. And now they can either be distinguishable or mixed, and both of these cases will actually reduce this visibility in a very same way. And actually from just a two-photon Hom dip, these two cases will just lead to exactly the same effect. Okay, so now we've learned from the previous experiment, three photons can be different. And what we did is we extended this experiment to, again, 3 photons. And we measured the photon number resolution, the photon number distribution here. So we measured how many photons do show up in each mode. And we varied the pairwise overlap. And the first setting we used is we used distinguishable pure photons that are to some degree distinguishable. So shown here to those familiar on the plus sphere, all photons kind of pointing upwards. And then we change the overlap by changing the partial distinguishability. And in the second set of experiments, we played with the mixedness of the photons. This is the experiment. So just in a nutshell, we have a fiber twitter, we generate single photons, and we measure here the photon number distribution. And now the interesting point is, what do we see? So we do the experiment for pure states, and we do it for mixed states. And we look at the outputs. And what is plotted here is now all the cases where we have 3 photons in one output, or 1 photon in each of the outputs. And what we see is that basically for this graph and this graph, we get again exactly the same behavior. But however, if we look at a partially bunched statistics, so where we have 2 photons in one output and 1 photon in the other, we see we get a clearly distinct behavior now for the pure state and the mixed state that we couldn't observe in the 2 photon case. So we again see that also for this pure versus mixed state interference, that 3 photons or 3 photon statistics show us a bit more than just the 2 photon statistics. And you can also understand why this is the case. I just throw some equations at you, but the important part is actually here, this blue part. So what you have to understand is that we have, again, the probabilities of measuring a certain output, and this depends, again, on all these overlaps. But now for the partially spun statistics, we have a volume here. And this is actually the volume spanned by the Bloch vectors. And now what you can create is a situation where for the pure states here, you have a volume that is non-zero, whereas your mixed state volume will always be zero. And as said, in the two photon case, this would exactly lead to the same results, whereas here we kind of see a difference in the statistics. Good, so this is what we have worked on recently in kind of photon interference. Just very briefly, we can also use photon interference to generate entanglement. And what we use is this kind of hybrid tritters, so these basically three mode equivalents of beam splitters. And the nice thing is now you can kind of play with your input states, and you can also measure your, in our case, polarization state here at the output. And to those working in kind of quantum information, you can show now, by just tuning the inputs here locally, you can generate different classes of entangled states here at the output, which is actually quite neat. And we can also verify that this works experimentally. And we also made some kind of work on some theory to how to expand this to more modes, to kind of n-partite splitters. And what we came up with is kind of schemes using these kind of networks to generate different types of entangled states. Okay, so with that, I'd like to kind of leave this first part and actually kind of hop to the quantum networks part. And when talking about quantum networks, we have hardware, so we have the physical systems, and we have software. And software is kind of the protocol, so the things you implement in a quantum network. And one crucial component of a quantum network is actually a Bell state measurement. Why is that? Let's just look at quantum teleportation. So we have Alice here in quantum teleportation. We have Bob here. They share an entangled state. And in order for Alice to teleport her qubit to Bob, she performs a Bell state measurement. So it's the crucial part of quantum teleportation. And this also then leads to quantum repeaters, to certain types of quantum key distribution. And it's also very important in photonic quantum computing. So the Bell state measurement is a very important part. The good news is it's usually very easy to implement. So in photonic systems, when we have like two photons and want to implement a Bell state measurement on them, I think many of you have done this. You take two photons, send them onto a beam splitter. So again, we have the Hongo-Mandel effect in some kind of way. And then we put like polarizing beam splitters here. In the case, we have kind of polarization qubits, and we put detectors here. And now we count how many photons are detected in each of the output. We record this, and dependent on what kind of input state we have, so these are certain types of Bell states. So depending on the state, we get a different output pattern. And this is plotted here. So the axis here basically just shows how many photons show up in which port, and this is the probabilities. And now we have 4 different Bell states, and what you have is that 2 Bell states here have a very distinct pattern, whereas those 2 have exactly the same pattern. And this is one challenge in photonic quantum technologies, and it means that the success probability of this Bell state measurement is limited to 50%. So you can't get beyond 50% unless you use nonlinear elements or you do some tricks with auxiliary states. And this is what I'd like to show you now. So what we do is we take the same setup and we expand it. So we add this part here, and we add 2 more photons in a certain state as shown here. And now again, we ask, how does the output statistics look like? And it's more complicated because we have more photons and more outputs. And now what you can see is, again, the green and the red states here have a very distinct pattern. We have again some overlap here, but you see that a certain percentage here of the orange and the blue states now can also be distinguished. And this means that you can boost by expanding the scheme the total success probability from 50 to 62%, still using linear optics and 2 additional photons. And this is what we implemented. This is how the setup looks like. I just go briefly through it for those working on experiments. We have a entangled state source, a Bell state source, using PPKTP, spontaneous parametric down conversion. We have our ancilla source here, creating this ancilla state. And then here we have the Bell state part, measurement part. So the first part here is our normal Bell state measurement, the first beam splitter here. And this is kind of the expanded version of it. And then we do kind of polarization measurements. We go to detectors, and in order to do photon number resolution, we split each mode into 8 different modes. And then we count the photons here. And first we do the kind of normal Bell state measurement with the setup. So we take out this additional part. We measure the statistics, and we see that, again, for the green and the red, get a distinct pattern, whereas here for those two, we get exactly the same pattern. And the color is kind of the measured data, and the black is the theory. And now we put our additional source in, turn it on, and we get this pattern here on the right-hand side, where you can see now here that for the green, for the orange and the blue, we get these kind of peaks that are distinct. So we can kind of uniquely identify them, or identify them in some of the cases, and this leads to overall enhanced success probability. We can analyze this even further, and there's kind of even more analysis on the results in this archive paper here, but overall we can show that we have achieved a Bell state measurement success probability of quite far over 50%. And now if you want to take this and put this in a quantum network, this becomes very relevant. Also, if you want to build quantum computers, because you need many of those Bell state measurements, and having efficient schemes to implement them becomes very important. Okay, and with that, I'd like to come to the kind of software part of quantum networks that we are working on as well. So the question is, when we have a quantum network, or if we have a quantum network, what do you actually do with it? So do you just want to do kind of bipartite quantum key distribution, or is there something more exciting you can do? And what we looked at is the conference key agreement. And this basically means you want to exchange a key in a whole quantum network. So let's say all of us are part of a quantum network, and we want to exchange a key. We want to have quantum security. You can do this, for example, by using, again, entanglement. And what you have to do is we have a large entangled state, and each of us gets 1 qubit of this entangled state. And now by measuring our qubit, we can establish a joint key. Of course, the kind of large state has to be the right state. There are some kind of ways how to kind of deal with this, but in general, we share an entangled state, and we all measure our qubit. And this has been proposed and also implemented. And there is quite also some recent work showing some kind of advantage of using entanglement in these networks over just using kind of bipartite links. What we looked at now is something even more. We looked at an anonymous version of it. So assume we are all in a big quantum network, but only a subset of us, let's say the PhD students, want to kind of arrange a kind of dinner tonight. And you don't want us, the PIs, to kind of know where your meeting place is. And this is basically the anonymous conference key agreement. So you want to share information in a part of a quantum network such that the parties participating are kept secret, and you kind of just share the information in a subset. And this is again possible by we all sharing a large-scale entangled state. And then those not participating in the key exchange measure their qubit in a certain way. So this is shown here. We start all having one big state. Then some parties remove themselves from the state, and then you, being part of this quantum network, perform some measurements for key exchange, and you can also do some verification checks in order to check whether those who are not meant to participate are actually kind of out of the state or out of the communication. And what you see again is that entanglement plays a crucial role, and again, multipartite entanglement. And what's very important now is when going from these kind of theoretical protocols to experiments is actually also to see how these behave under noise, realistic conditions. And what we did is here a first test of this protocol with 4 qubits, so 4-qubit quantum network, 4 parties, and we had like 3 parties communicating. And we also measured what would happen if we just have 2 parties communicate in this network. And what we could show is, yes, we could generate a key with probability of 95% here. And these are the kind of different colors here for different configurations of the network. We could also perform verification, so checks whether anything is going wrong, whether we have an eavesdropper. And we could also analyze the probability that we have actually an eavesdropper and we don't detect. And this can be also bound to some values. And then, so the protocol so far was using large-scale entangled GHZ states, so a certain type of entangled state. And then you can ask yourself, can we actually use also other forms of entangled states to do this? And recently we looked at cluster states that are also relevant in the context of quantum computing. And we looked at some protocols and implemented some protocols using kind of this linear type of cluster states for quantum communication. And this is again a linear optical setup to generate these type of cluster states. Again, we looked at the key exchange. So we have a linear network shared between the parties. You can check like how likely is it to generate the correct key, how likely is it to have an eavesdropper. And you can also take this protocol and actually exchange a very, very long key. That's what we did here. And this key was kind of long enough for us to encrypt the group logo. So Alice took the logo, took our key, encrypted it, and then Bob and Charlie took their parts of the key and decrypted it. And you see very nicely, of course, we don't have perfect experiments. You can see some kind of noise, but you also can clearly see the picture. And now you can also take this and implement error correction on it and privacy amplification. And this is kind of, if you're interested, also mentioned in this work, but I won't go into detail here. So basically, I've shown you kind of 3 aspects of the work we do in my group. The first, going deep into kind of quantum optics and the foundations, looking at interference in a slightly different way, showing that 3 photons are something more than 2 photons, and that we have effects that we can observe in 2-photon interference that we can't see that we can observe in 3-photon interference that we can't see in 2-photon interference. And I've shown you 2 parts of a quantum network, both on the hardware side and the software side. It's important to say you can go even further with these Bell-set measurements, quite easily to 75% by adding more photons. And there are also other kind of protocols how you can go in principle to kind of close to probability of 1. I also hope I've shown you that when we have quantum networks, we also need to think about what we actually do with them. Multipartite key exchange is one example, but we see that also, again, entanglement and different types of entangled states play a very important role in these kind of quantum networks. And with that, I'd like to kind of end. Thank you, my group, especially those people contributing to this works, and also our collaborators on these kind of 3 specific topics. And I've promised in the beginning, I say a few words on these other topics. We also work on integrated quantum photonics and photonic quantum computing. If you're interested, have a look at our website. In particular, we're interested in kind of building small-scale silicon photonic circuits to implement quantum computing in networks. So not just doing communication in networks, but also quantum computing. And PhotonQ here is a project that we just started this year. Also, for example, with John here, being involved aiming at building photonic quantum processors. And with that, I'd really like to end. If you like what we do, get in touch. We have also some open positions at Stuttgart on photonic quantum technologies. Thank you very much.
Yeah, thank you very much for the nice talk and also the effort to give a longer introduction to the mixed audience. We have time for questions.
Thank you for the talk. I have a question. You showed some of these percentages by which you violate, I think, Bell test or so, that you use to quantify the entanglement. And I wonder what limits those percentages. What are your errors, basically?
You mean in the Bell state experiments? Many things. So one thing is distinguishability of the photons. So as I said, in these Hongo-Mandel experiments, you need pure and indistinguishable photons in all kinds of degrees of freedom. So any kind of distinguishable factor you have, frequency, spatial overlap, anything leads to kind of reduction in the sum visibility, and in turn leads to kind of a lower visibility, a lower percentage. The other factor that we have in our experiments is that we use parametric down conversion sources. So what we have is, in a certain number of cases, we not just have like the number of photons we expect to have, but we have additional photons in our circuit, and these lead to noise. And these could, however, be kind of reduced by using true single photon sources. So any photon sources that emit a single photon and not with a certain probability, a higher number. And these are kind of the two main factors here that limit us.
Other questions?
I was intrigued by the picture that you shared in your experimental, so your group logo that you shared in your experimental work. And that kind of triggered in myself the question to which kind of quality you need to transport information that we can reconstruct it, and if this is already basically in this, yeah, the picture of your group logo, which you kind of
okay, the Loop logo. Yeah.
Because the group logo, so
yeah.
it's super impressive, don't get me wrong. So, but the group
yeah.
logo has noise at the end.
Yeah.
So
it's this here, right? So we have 83.5% probability that a key bit is correct. And this is, I mean, when you implement this in the picture, it's kind of very nice because your eyes or your brain filters out what you want to see and you can still read it. You have to imagine basically every pixel here as a single bit that is shared. And this means we have kind of 83% of bits that are correct and the rest has kind of an error. What we do, however, you can use this method to exchange the key and then implement methods for error correction. And this means kind of from this like large key you have, you reduce it to a much smaller key, but you kind of do some error correction on it. And this is what you would do in practice actually. So we also kind of did this in the paper. But what it means is you need to exchange much more key than you can actually have in the end to kind of encrypt your message.
And you're talking now about classical error correction or? Okay.
So Stefanie, thanks very much for the great talk. So I had a question which relates to when you showed the Bell state measurement, you showed with the ancilla photons, you can improve the efficiency of the Bell state measurement. And also in terms of, let's say, the output map that you measure, it becomes more complex. And it also becomes kind of, it develops unusual features to distinguish between the 4 Bell states. So when you go further than that and you do it again with 2 more photons, do you get to a situation where each of the Bell state has a unique feature, or would you always have to measure all possible output modes?
So in the limit, you can, in principle, get to 100% of kind of distinguishability of the different Bell state at the limit of having an enormous number of extra photons and an enormous number of extra modes. And this is kind of also a bit the trade-off. But what I think is nice that by just adding, so the kind of initial steps, that by adding few more photons, you can get easily much higher in the probability. And when you look at the schemes for quantum computing, these kind of steps of like 10 or 20 more percent actually can make a difference already. So there's this kind of trade-off for how big you want to blow up the scheme and how big your advantage then is in terms of using it.
There you could, let's say, that's kind of fingerprint of that particular Bell state.
Yeah.
Those 3 events, say if I see those 3 events next to each other, that it's likely to be.
Yeah, I mean, this is a tiny bit misleading, because what we do is, what you probably noticed, is we do some pseudo photon number resolution here. So we kind of rely on the fact that when we have photons coming in here, they kind of split up onto different modes. And this means you have some kind of distribution you get here. If you had like proper photon number resolution, in the sense, if you had a detector which could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then the pattern would look slightly different.
Okay, at this point, I don't see any further questions. So I'd like to thank Stefanie
Thank
and
you.
all the rest of the speakers of the day.